Hi there, let's look at aldol reactions. So here, ald coming from actually aldehyde or ketones. So that means there is a carbonyl group functionality, C double bond O. OL all for the alcohol, the OH functionality. So you do have RC double bond OR, OH for aldehyde or ketone, and ROH for alcohol. So these are the ones involved in an aldol reaction. Now we're going to look at mechanistically what's the important things. So electrophile E plus should be there, and nucleophile Nu minus should be there in order to do a reaction, because this reaction will make a carbon to carbon connection. So there's a electrophile and nucleophile combining. So those are the key things. Carbonyl and an alcohol is formed, and electrophile and nucleophile should be there, and reagents are bases. The bases are could be hydroxide, could be tertiary butoxide. That's a larger bulky base, and so those are the good bases. Lithium aluminum hydride also a good base. Now let's look at another important thing, because I was talking about the bases. Right? So here, if you label this carbon chain, carbonyl functionality, alpha, beta, gamma, delta, epsilon, it goes to the both sides. So if you have more carbons, you can label more. This is the old-fashioned way. But look at the alpha position, you have hydrogens. So these are called alpha hydrogens. I call them alpha hydrogens are acidic. Now you see why we have a base. So the base is actually to extract this alpha hydrogen and to make a carbanion here on the alpha position. So I kind of neglect the rest of it. So you make a carbanion at the alpha carbon by extracting the alpha hydrogen by a base. So this carbanion can actually make resonance structures by pushing the negative to the oxygen, because oxygen is electronegative. So you make this compound, this ion actually. So this is the O negative. It's much tolerated. And here is the double bond ene, and here is the O negative, is called olate. So that's how you get enolate. So you do make an enolate from a carbonyl with the reaction of a base. So this enolate is stabilized by resonance action. So we do have this A and B two resonance structures, but we know resonance structures are not real. They are just on the paper. So you're never going to find a resonance structure in a test tube. So it just we just think that's easy way to explain, right? The real structure is in between. Okay. Now, so if I imagine I have this nucleophile, the enolate, and I'm going to react with an electrophile. Let's see where the electrophile. I'm putting in white. Here's the delta minus and delta plus. The carbonyl, normally carbonyl behaves as an electrophile, the carbon of the carbonyl. So therefore, now you have a nucleophile and the electrophile. We can attack from this negative to the electrophile. So that's how you make the carbon to carbon bond. So let's copy the electrophilic portion of the reaction. That's here, and the O negative is created, and then the nucleophilic portion is here in yellow, and then we connected with the yellow bond a new bond. So that's how we make the carbon-carbon bond. Now olate always going to catch a proton if there is availability, or it's going to sit with the cation. Okay, now we have the aldol actually. So you see the aldehyde functionality, the carbonyl there, and the ol there. Now we have more bases, and we're going to attack this alpha hydrogen again, take it out, and then kicks out the OH minus. So what you make is actually another double bond here. So now you make, with the in between the two carbon chains, you make an extra double bond that's actually in the position of alpha and beta. So we call this is alpha beta unsaturated compound. So that's the end product of an aldol reaction. Now we can, so that's details. Now we can look at in a different way a few examples, and also let's take this example here. So let's say I have a carbonyl, and this carbonyl I'm showing the alpha hydrogens, and then the other carbonyl has a R2 functionality, just to show the difference, and this one has alpha hydrogens too. But it's an easy way to look at the base, and if I have heat, what happens is this base triggers this taking out the alpha hydrogens, and together with the oxygen on the carbonyl, you're going to remove a water molecule, minus water. So now you created the double bond in between the green chain and the yellow chain. So that's the easy way, a shortcut to go to the end product alpha beta unsaturated. Got it? So in one step, you need only the answer, then this is the way to go. So you highlight the alpha hydrogens, you highlight the carbonyl functionality, take a water molecule out. So you need to identify A and B, A for the nucleophile, B for the carbonyl, right? Okay, now what can you do? You can actually mathematically combine A to the B, B to the A to the A, B to the B. Now this is going to give you a terrible mixture. Now we don't want in reactions terrible mixtures, right? We want to have our target product. So what do? So we can actually control that. So how do you control? We can have carbonyls without alpha hydrogens. So now this carbonyl can react only as the electrophile. So that's the electrophile, delta plus on the carbon and delta minus on the oxygen. So therefore this one exclusively no alpha hydrogens. Now let's find out a nucleophile. Now you can get something like acetone. So there's two sides of alpha hydrogens, doesn't really matter because it's symmetric. So now you put the base and the heat, and you're going to create the double bond, right? So that's the end product of aldol. So you're going to make alpha beta unsaturated. I just put it in light blue here so you can see where the skeletal came from, right? So that's the exclusive specialization, specificity there. So you are only connecting A to the B because electrophile is specialized, specified, and the nucleophile is specified. So therefore you're going to get only A to the B. You got the idea, right? So now you see you can just change the R groups, and you can have limitations, therefore you will get a target product. Now we can look at few other examples. Let's take this one. So let's say I have an aldehyde without alpha hydrogens again. See, this hydrogen here is not an alpha hydrogen, it's a carbonyl hydrogen, right? So that's not an alpha. But second one has alpha hydrogen, 3 of them, and you put the base, heat it, and then you're going to remove the 2 hydrogens from the alpha hydrogens and then the oxygen from the electrophile. So you get alpha beta unsaturated compound. Again, it's only one product. So see the 2 examples, the green one and the yellow one. So you do have only one product. So this is how you do a reaction selectively, right? Now let's talk about another thing. So this is going forward alpha beta unsaturated products, but you can go backward. That is called the retro Aldol reactions. What do? You heat with water. Look at this one. I put exclusively the water molecule in between the double bond of alpha beta and cross-cut through that double bond, and you get the reactants. So you can do the same thing for this green one. So you put the water molecule in between the alpha beta double bond, cut through that alpha beta double bond, and put the oxygen in red to the electrophile and 2 hydrogens onto the other one. So you can do here too. So put the water molecule in between the double bond alpha beta, and oxygen solid red goes into the electrophile, and 2 hydrogens goes to the nucleophile. Okay, all right, so that's the retro aldol reaction. So basically going backward. So I would kind of learn, when you do aldol going forward, you make sure carbonyl and alcohol presence, and electrophile and nucleophile identified, and then base reaction, and then make the alpha beta unsaturation. Going backward, retro aldol, so you just need to find out the alpha beta unsaturated double bond and cut that through across, and then put a water molecule to make sure you make 2 carbonyls, right? So your end product should have 2 carbonyls. That's the goal. Now let's look at another thing here. So a little bit more details, you may need it. So this one actually doesn't go directly to the alpha beta unsaturated. What you make is in between this compound. This one is actually β-hydroxy compound. So this β-hydroxy compound is in between, but you can have this ald and the ol. You see that? You see the aldehyde functionality, you see the alcohol functionality. That's why we call the aldol. So the very end product, which is the alpha beta unsaturated, is only you're getting when you have heat. Now in this step, what do? You have this water molecule removed in between alpha and beta. You participate the base to extract the hydrogen, proton, and kick out or remove a water molecule, and you make alpha beta unsaturated compound. You can go back the same way. So you add water and heat it, and you add the water molecule in between.